Okay, I guess I can start, right? Sorry? 1 more minute? No, sorry. Yes, no, maybe. What do you want me to check? The time? 48. Oh, okay. Yeah, I didn't hear when you said, at the time you said that we were going to start. You said 10 before, you know. Well, but a little bit of cheating is okay. So. Okay. All right, so yesterday I forgot to mention that many of the things that I'm talking about are in 2 books already, one by Heng and Plevka and the other one by Elvan and Huang. And of course, I've been informed that the TASI 2014 lectures are coming out soon. So that probably contains 80% of what I'm going to say, or what I'm going to say today, at least. Probably none of this will contain what I'm going to say tomorrow or the day after tomorrow. So that's why you have to come. Okay? And you're already here, so please don't leave. So yesterday, we were talking mainly about the scattering of gluons in a UN gauge theory. I hope I was able to convince you that there is a way to manage the color structure of the amplitude. Each gluon comes with a color index, and there was a way to extract all the color information and arrange it in single trace terms multiplied by some kinematic factor. And that kinematic factor, we gave a name. We call it capital A, and we denoted the full amplitude as calligraphic A. Now, these are called partial amplitudes. And they depend on the order that we choose. Of course, it's some permutation of n elements modulo cyclic transformations. And yesterday I asked how many terms would there be in this sum, and you correctly answered, and you said that there would be n minus 1 factorial terms. So in principle, one has to compute n minus 1 factorial partial amplitudes. Very good. These partial amplitudes, if you fix one, so we usually take the canonical ordering. These are the objects that have been studied in great detail in the past 10 years. So there are many different approaches. So yesterday you saw that there is a connection of these objects with Wilson loops. And integrability. These objects were the seed or the motivation for a construction that is called the BCFW construction, which I'm going to talk a little bit about today, following a recommendation of one of the organizers. So this BCFW construction led to a construction that is called the Grossmanian construction. And this Grossmanian construction led to something that you might have heard, which is called the Amplitude Theorem. Okay. This Grossmanian construction makes manifest that n equals 4 super Young Mills possesses something that is called a Yang-Yang symmetry, which is much larger than the superconformal group that we all know it should possess. In fact, this is an infinite dimensional algebra. However, as exciting as all this sounds, there is something that the partial amplitudes do that these representations don't quite tell you. So they have their own little secret. They actually like to talk to each other. So partial amplitudes like to talk among themselves. So what do I mean by that? Well, here I'll have to write the names because they're not very easy to spell. But one way they talk to each other is through something that is called the Claes-Kuijf relation, discovered in 1989. And the relation says that these partial amplitudes, even though they are multiplying these traces, and the traces are independent, these are independent if you take n to be large, much larger than the number of elements or the number of particles that you are scattering, these traces are very independent objects. So you might think that these partial amplitudes are also independent objects. But, as they are called, these guys discover what are called the KK relations. And these are relations. Sorry, they went into the black hole. These relations tell you that if you take a partial amplitude with the following ordering, you take particle 1, you choose particle n, and you sprinkle the other particles in between in a way that can be completely up to you. So I'm just going to call it alpha, and I'm going to call it beta. These are sets of particle labels that I'm sprinkling here and here. So the relation that they discovered is that this is equal to -1 to the number of elements in beta, a sum of partial amplitudes where the label 1, of course, we can choose the label 1 to always be first, because all partial amplitudes must be cyclic. They have to respect the symmetry of the trace. So it's trivial that we can put particle 1 to be first. What is non-trivial is that kk tells us that we can always choose to write any amplitude in such a way that particle 1 is first, and very nicely, particle n can be last. Now, this is a linear combination, and the linear combination has some permutation here of n-2 elements. But which permutations you have to put in there? Those are permutations that are called order-preserving permutations. So what do they mean? They mean the following. You take all the sets, all the particle labels in alpha. You take the particle labels in beta. You take the set beta and you transpose it. Okay, so you change, you reflect it. Now you mix the two sets of labels that you got in that way in all possible ways, but preserving the relative order of the particles in alpha and the particles in the particles in beta transpose. Meaning, if one particle was first and the other one in the order alpha, they would always stay like that, even though you sprinkle particles the beta transpose in between. Okay, so let me give you an example. So I'm going to give you an example of the following form. We're going to take 1, 2, all the way to n-2, then n, and n-1. Okay? So what is my set alpha? My set alpha is this one. And what is my set beta? This is my set beta. So I'm going to show you that we can use that relation to write this, or I'm going to use that relation to do the following. Now, the number of elements in beta is 1, so there is a minus sign. There is something remarkable. All the coefficients here are +1. This is not a schematic. This is exact. So there is a minus sign. And then you can put here a1, comma. So I have to put n at the end. And here, all these order-preserving permutations of alpha with label n-1. Okay? But what do I mean by that? Well, it's very easy. I just have 1. I put all these guys to all the way to n-2. Then I have n-1 and n. So this is alpha, and this is my beta. This is the first element, I would say. The next element is a, 1, 2. Now I put n-2, say n-3, and then I put n-1, n-2, and n. You see what is happening? I'm moving this particle n-1. I'm moving it in positions. What's going to be the last term? Can anybody guess? Or, well, you don't have to guess. You have to. Sorry. So the last term, all I'm doing is moving this particle in different positions inside alpha. So this particle is infiltrating the permutation alpha. The first time is here. The next time it goes here. So it keeps going all the way to reaching the position next to 1. And then I have 2, 3, all the way to n minus 2, and then particle n. Okay? Now there is something nice. If you move all those guys to the other side, you get a relation that tells you that if you have any particle, say we put it on with n here and n minus 1, and you sum over all the ways of moving this particle around, so all the ways of moving that particle around, keeping the other ones fixed, that's another interpretation of the same formula. You get 0. Okay? So all these partial amplitudes are supposed to know about the other ones. They are supposed to be friends in such a way that when you add them up, you get 0. Does this formula have any physical meaning? You may ask. Well, it does. Here is a physical meaning. Take the label or the color structure of particle n minus 1 and declare that particle n minus 1, remember our gauge group is un, so un has a factor that is u1 and another factor that is sun. So you can choose your gluons to be in any of the n squared generators. So I just happen to choose my gluon an minus 1 to be the generator of u1. So the gluon, or now it's not a gluon, the particle n minus 1 happens to be a photon. So what do you think is the amplitude for producing a photon out of n minus 1 gluons? What should that amplitude be? Exactly, 0. I mean, somebody was telling me the answer, but without just... Yes, indeed. So this amplitude, if you have a photon, if this guy is a photon, this should be 0. But how can that possibly be? We have this sum of all these independent objects, or they seem to be independent. But note the following. If this trace is the identity, many of these traces that I already had there become identical. Which ones are identical? Well, I can now start collecting things like this. Let's look at the coefficient of Ta1, Ta2, Tan minus 2, and Tan. Tan minus 1 became the identity, so it could be anywhere inside here. So I can now collect all the terms that had this guy sitting anywhere along the trace. They all come out with the same trace structure. So this object multiplies this combination that I have there with coefficients exactly equal to 1. But I just told you that kk told us that this thing has to be 0. So this is 0. And likewise for any other combinations. So this identity, or this particular instance of the kk relations, is called, very nicely, the U1 decoupling identity. Okay? Now, if you're only working with a single partial amplitude, and you're basing everything on that particular ordering, you're going to be obscuring these relations. Okay? But of course, you're going to be making other properties manifest. So these are the signs, or these are the standard properties of dual descriptions. Sometimes you have this description of the same physical system, and you have another description of the same physical system. And these two descriptions, although equivalent because they are describing the same object, they allow you to see different things. Okay? So, after this, we're going to move on. It's a little bit inconsistent that I already told you all this about things that happen among partial amplitudes. And the next thing that I'm going to do is to discuss BCFW for a single partial amplitude. But hopefully today we will have time to continue with what we did yesterday, which was our way to walk towards the twistor string construction that we can develop as a generalization of Nair's vision. And that twistor string formula will make these properties completely manifest. Okay? So that's where we are heading. So right now, you can think that we're going to have a small aside from our main course of action. So we're going to start discussing BCFW, but before I do that, I'll give you an exercise. And the exercise is find the physical meaning of all the other relations. So I gave you the physical meaning of one. So find the physical meaning of all these relations. Okay.
Are these tree-level relations, or they won't have root level?
Yeah, these ones are tree-level relations, right now as I'm stating them. Okay.
But the one decoupling is over plus.
Yes. Yeah, the fact that the photon has to decouple, it's at all orders in perturbation theory.
Do we not have the decoupling identity?
Sorry?
Do we not have the decoupling identity of SUN?
So you see, this answer, all the particles could be gluons. So this is the answer, also the answer for SUN. But you can derive the fact that these partial amplitudes satisfy these properties by extending that to be UN. Okay? Of course, the derivation of these single trace terms relied on the fact that we had UN. Otherwise, this fusing identity will also have another term. So you will have to take that into account. So if you're only dealing with SUN, you might have higher order traces. But the leading order traces, they will all behave exactly in the same way. Okay. So this is an aside, which might take us a little bit, but let's see. So this is something that we found in 2005. Which is a fairly simple construction, but it ended up being something very powerful. So that's the kind of things that you are very lucky if you find one. So something that is trivial but powerful. Now, before we discuss this, let's review a little bit what we know about the 3-point amplitudes. So I hope you remember our friend, the 3-point amplitude with 2 negative helicity and 1 positive helicity. This was an object of this form. We didn't get to write it, but we could also have done this one. Okay? And we also didn't write it, but we could also have done this. What do you think this one is? Well, once again, it can only be a function of the angular brackets or the square brackets, but not both, right? And it has to have certain properties, right, under rescalings of lambdas and lambda tildes, so that it has the proper helicity. So this object will end up being, you can show that it's unique, and is given by this quantity. Likewise, this object is given by this. Now note that these two sets, they have different dimensions, right? So wherever the coupling is, if I put the coupling again, the couplings cannot be the same kind of couplings. So it turns out that these couplings, the G, is dimensionless. And this coupling is dimensionful. Okay. So, well, you can easily check that these are the couplings that will come from an F-squared term. Okay. So if you just say that you want a theory of interacting helicity plus or minus 1 particles with a dimensionless coupling, you only have these two kind of vertices, or these two kind of 3-particle amplitudes. But if you want to include F-cubed terms, you can also have this kind. In today's lecture, we're going to set this coupling to 0 because we're only dealing with pure Young-Mills. Yes?
Is it not possible to have some theory that would reduce terms through away?
You see, the terms that I threw away are terms that when you restrict yourself to real Minkowski space, they blow up. So they are unphysical. So there is no way, I don't think there could be any way to write down a Lagrangian, at least a local Lagrangian that would do that. And even if you did and it's non-local, it wouldn't be physical. But there is something interesting. If the 3 particles are scalars, try to work out what happens if they have helicity 0. Okay? Okay. So for today, these amplitudes are given by this, where G is going to be set to 1. So we're going to set G to 1. G tilde is going to be set to 0. So every time we see something like this, we have to set it to 0. Okay, so next. So we realize that at least at 3 level, all these partial amplitudes are nothing but functions that are rational. So these are rational functions of these SL to C invariant objects. So if you have a rational function, you can ask yourself, well, if I only knew all the singularity structure, if I only knew all the poles and all the residues of this rational function, I can construct it. Now the downside is that this is a rational function in many complex variables. So you will have to know its behavior in a big complex dimensional space, and then do multidimensional complex residues. That could be done, but it turns out to be unnecessary. So what we want to do is to restrict this complexity to the minimal possible one. So we want to find a 1-parameter deformation of the data such that our amplitude still remains on shell. A is still an on-shell physical amplitude. So I told you there are many books already about this. So I'm not going to try to motivate it. I'm just going to give you the answer. So one possibility, there are many possibilities. So one possibility is the following. So let's deform the spinner. Now I'm going to use a shorthand notation. Yesterday, I was very careful to, every time I was writing a spinner, I would write the index alpha. Now, I'll trust that you know that lambda means a two-component object, okay? And lambda tilde as well is a two-component object. So when I write lambda 1, I don't mean the first component of lambda. I mean the spinner of particle 1, okay? And this is a two-component object. And as somebody reminded me yesterday, I didn't mention it, but these are just pairs of complex numbers. They are not Grassmann variables, okay? So you are right in remembering that when you have spinners, we usually think about also having Grassmann numbers or Grassmann variables somewhere, but that's when you quantize a field. So if you quantize a field that is in the spinor representation, you are supposed to dress the wave functions, which are bosonic objects like these ones, with creation and annihilation operators whose anti-commutation relations are given, okay? But don't confuse the two things. These are the wave functions. So these are just pairs of complex numbers. So let's deform this by a single complex variable. And this will look strange, but you will see the reason. So we're going to do something very violent, it seems. We're mixing the spinor of the first particle with the spinor of the nth particle. That seems to be a very non-local thing to do. And indeed it is. Okay? And all others are unchanged. Okay? Now, the first observation. All momenta are null. You'd say, how is that possible? You changed this. Well, but look at the momentum of particle 1, now written in terms of alpha and alpha tilde as a function of z. This is still a spinor, lambda 1 of z, with index alpha, now I'm writing it explicitly, times the antiholomorphic one, lambda 1. If you compute the determinant of this matrix, the determinant is still 0, no matter which value z you choose, because still written as a tensor product of two vectors, of two two-dimensional objects, okay? So the determinant of k1 of z is 0 for all z. And same thing happens for kn. So even though I've deformed the data, I've done it in such a way that the particles are still on shell. So that's very nice. But what else? If I want my amplitude to remain a physical amplitude, I told you that amplitudes are not functions, they are distributions. And the reason is that they have to satisfy, or they are only non-zero, on kinematic data that satisfy momentum conservation. So if I violate momentum conservation with my deformation, I cannot keep saying that my amplitude is a physical one, and I cannot use all the properties that I know physical amplitudes satisfy. So momentum conservation is a statement that Ka has to be, the sum has to be 0. Okay? So I just have to worry about K1 that was deformed by Z, K2, nothing happened to it, and Kn minus 1, nothing happened to it. Kn was deformed by Z. And the question is this 0? Okay? Well, let's look at this term and this term in more detail. So I'm going to write this explicitly now as a bispinor. going to write lambda 1 of z times lambda tilde 1 plus all these terms, and this is lambda n times lambda tilde n of z. Now I'm going to write this explicitly. So if you look on the other blackboard, this has a term that comes and multiplies as the first one, plus z lambda n times lambda 1 tilde. On this side, I'm going to get lambda n, substituting this from the other blackboard, I get lambda tilde n. Now you see why I chose a minus sign, right? Minus z lambda n lambda 1 tilde. So what happens? What happens is that if my original data, the undeformed data, satisfies momentum conservation, so does the deformed data for any value z. Okay? So this is true for all z's. Now I have a function, so my amplitude, my partial amplitude, has now become a function of z, and not only that, it's a physical amplitude for any value of z. Okay? Now I want to compute, my object of interest is this, so we are interested in this. So there is a trivial way of obtaining this from this function of z. What's the trivial way of doing it? Well, you set z to 0, right? But there is a more elegant way of doing it. You say, no, that's a little boring. I really want to do something more exciting. So I want to show my friends that I know complex analysis. So I do this. That's much more elegant. I hope you agree, right? So this is a very, very, very elegant way of setting this to 0. However, it turns out to also be useful. Yeah. No, you see, that shows a different level already. I mean, the moment when you set 2 pi i's to 1, you're at a different level. Yes. The standard one. Okay, we can say this is a cool one. Good. Okay. But of course, you wouldn't know complex analysis unless you knew about the residue theorem, Cauchy's residue theorem. Now you say, now on my complex plane z, I've constructed a rational function that has a pole at z equals to 0. I mean, the pole is obvious. I put it in by hand, right? So this function has a pole here at z equals to 0, and my contour, which I have defined here, is a tiny circle around here. Okay? But my rational function could also have other poles. Okay? And therefore, I can use a residue theorem to write this amplitude as minus the sum of the same integral over all other poles. Okay? So I just deform the contour, and I end up, so I deform the contour and end up picking up these residues and even going all the way to infinity. I could also pick up a pole at infinity if there was one. Okay? Very good. Now, this would be a completely useless exercise unless we had information about what the other poles are. But now we can have, so I'm using the chance that I'm giving this lecture before Pedro's lecture, because he's going to tell you complete lies. He's going to tell you that, no, there are no poles and all these things and so on. Okay, that's fine. But for the time being, I know you're doing it non-perturbatively for any value of the coupling. Here we're very, very close to lambda equals to 0. We're doing this at 3 level and so on. So for us, good old-fashioned quantum field theory, there is a pole every time a propagator of this form goes to 0. So this is a pole of A1 to up to n. Okay? Why only those? Aren't those very weird? I just chose a particular label and added some of them in a consecutive order. So only those poles can possibly appear. The reason is that we are dealing with partial order amplitudes. Okay? So these particles are supposed to be labeled, labels on a circle. And the Feynman diagrams that contribute to this amplitude, to this particular coefficient of a color structure, are those that can be drawn on a plane with these external particles getting out and hitting these labels. So you can convince yourself, well, what kind of propagators can I have? Well, there is a Feynman diagram that looks like this. Should I have K1 plus K2 squared? Now K3 can join in. Now this one is K1 plus K2 plus K3 squared. Now, can I put this one before this one? No, because then I will have a non-planar diagram, right? So if I try to put this one here and this one later, this one will have to cross this line and get a non-planar diagram. But that will not contribute to this particular object. So this label has to come somewhere here. Okay? Very good. So these are the only possibilities for poles of the function A as a function of the spinors lambdas and lambda tildes. But how about as a function of Z? Z is the only thing that is interesting to us. Okay? So poles in Z. That's what we want. We don't care about poles of this function as a function of lambda 4. Okay? Well, certainly these poles will come from the poles that we already had, but only from the ones that develop a dependence in Z. So if we have, say, K1 of Z plus K2 all the way to some Km squared, this object definitely depends on Z, and this would be a pole. But what happens if by any chance I start with something, say, Km minus 2, Km minus 1, I have Kn of Z, and I have K1 of Z, and K2. Is this a pole as a function of Z? Look at the blackboard over here. No, it doesn't depend on Z. So this is Z independent. So no pole. So that's remarkable. It's remarkable that our deformation is only choosing certain poles. Well, that's not remarkable. That's a fact. It would be remarkable if that was useful for something. So the number of poles on the complex plane, in addition to this one at 0, is a very small number compared to all the possible propagators that you have in your amplitude. So those are the poles. Except that we're forgetting something. How about Z equals to infinity? Well, if we can show that this object goes like something over Z as Z goes to infinity, then automatically this integral on a contour around infinity will give us 0, because this will make the object go like 1 over z squared, and we will get no pole at infinity. So if our amplitude vanishes fast enough, or it doesn't even have to be fast enough, if it simply vanishes as you take z to infinity, then we will be happy. Note that that means taking the momenta in a particular direction and making those two particles to be extremely hard particles. So all the other particles become a soft background. So these two particles are becoming very, very hard. And we want the object to actually vanish in that limit. Does it always happen? The answer is no. It doesn't always happen. You have to be a little lucky. Or clever, depending on your choice. Look in your notes at the polarization vectors we had yesterday in a spin or helicity form. Okay? And look at the polarization vector for particle 1 with negative helicity, written in bi-spinor notation. Okay? So if we make the substitution that we have over there on this object, what do we get? As a function of z, when z goes to infinity. As z goes to infinity, how does this object behave? 2 seconds? 2, 1, 0. Okay, time's up. So it goes like order z. So that doesn't look very promising. But how about this one? What happens if the helicity of particle 1 was positive? Exactly. So that looks very, very good. Excellent. Now we can repeat the same exercise for particle n. And you can see that this one goes like this, and this one goes like this. So now you see in which cases you can be lucky and which cases would be the unfortunate ones. Well, with that particular choice of the formation, I better do that only when this happens, when this helicity is a helicity of particle 1, and particle n has this helicity. When that happens, you can show, by using Feynman diagram arguments, that your amplitude always vanishes when z goes to infinity. The polarization vectors are helping you to make that happen. So I didn't say it here, but we're going to choose the helicity of particle 1 to be +1 and the helicity of particle n to be minus. So people have generalized this in tons of possible ways. They have explored the range of possibilities, how this can be applied to different theories, gravity, quarks, massive theories. So you name it. There was a recent paper claiming that all renormalizable theories can be constructed in similar ways to these ones. But for that, I'll let you read the books. Okay, so let's continue with this and assume that we're doing those helicities. Okay. Very good. So now we are done with this part. We have complete control of the pole structure. So we know exactly where this function a of z has poles, and moreover, a of z over z has poles. Okay? And there is nothing at infinity. Now, if we only knew the residues, we would then be able to construct the function completely, right? Because this is nothing but the residue of a of z over z at z equals to one of the physical poles. Let me put it like this so that people at the back can see. So A of 0, or our physical amplitude that we want to construct, would be equal to a sum over residues. Okay. Now, do we know the residues? Well, first of all, the fact that we only had poles of this form follows from locality. And the kind of residues we're going to get follows from unitarity. So we're using the two basic principles of quantum field theory to construct this object. So let's do it over here. So unitarity implies is that as you approach one of the poles, as a propagator goes to 0, your amplitude, let me now denote it as a blob, factorizes. So this is what the picture that Pedro was telling you yesterday. So the amplitude will factorize. Note that whenever I draw Feynman diagrams, I usually use wiggly lines, right? Here I'm not using wiggly lines. And the reason is that every line you see, so any line is on shell. Okay? So this doesn't mean a propagator. This means an on-shell particle that propagates from this amplitude to this amplitude, okay, from this object to this object. So these particles are interacting. So these particles are the ones that make up this P. So this P is the sum of some momenta, say A belonging to some set. And these particles here are the particles in the set I. And these particles here are the particles in the complement. So very nicely, as you approach a pole, the amplitude factorizes into two on-shell amplitudes. Now, unitarity also tells you that the particle that propagates here has to be any possible particle in your theory. Okay? So you actually have to sum over all possible helicity values for this particle. In this case, we only have particles of helicity plus minus 1, so you have to sum over plus minus 1. If we had color, we have to sum over all possible color structures, but for us, color is not an issue. We are colorblind, meaning that all the color structure has been stripped out, so there is no color structure here. We only sum our helicities and we're done. Okay? Well, that is, well, what unitarity tells us is that this behaves like this times 1 over p squared. So the coefficient of the pole is given by this object. And that coefficient is then the residue that we're looking for. Okay? So our amplitude is going to be given by that object. So you can show that precisely at the value of z, well, you have to do the calculation, but I'm just going to give you the answer. So you have to sum over all possible factorizations. We know we have, this is fine, particle 1, okay? Particle 1 with a hat, because the momentum of particle 1 is a very strange looking object. The momentum of particle 1 at the value, at the location of the pole, is given by this object with z given by the value of the pole at the location of the pole. So this object is a deformed momentum. So you now have 2, 3, all the way up to m plus 1, m plus 2, all the way up to particle n, which is also deformed. Okay? You can show that the z in this formula conspires to precisely give you, when you evaluate at the residue, the value of the propagator, k1 plus k2 up to km squared, completely undeformed. Okay? So that's the answer of using unitarity and using this formula. Okay? So I'll give you this as an exercise. Carry out the whole calculation and show that this is the answer. Now, m goes from where? Well, you need at least 2 particles here, right? Otherwise, you don't have a factorization. So m goes from 2, and you need at least 2 particles here, okay? So m goes up to where? So it's some function of n minus something. So if m, I need this m minus 1, so m has to be m minus 2, right? Okay, so this is the formula. Now, why is this formula interesting? Well, let me put here plus and minus to remind us of the helicity. We have written an m particle amplitude as a sum of products of a smaller particle amplitudes, okay? Amplitudes with a smaller number of particles. And they are completely on shell. Remember, this particle is on shell. And I forgot to sum over helicities. So there is also a sum h plus minus 1. So if you know lower point amplitudes, you can construct the higher point ones by using this, because this became a recursion relation. Okay. Now, there is a generalization of this recursion relation to loop level that allows you to construct the integrand of a loop amplitude in n equals 4 super Young mills by precisely using the same structure. Now, you would say at loop level, this is crazy. At loop level, you must have dilogarithms, polylogarithms, maybe Goncharov polylogarithms. crazy things that are not even motivic, who knows. This is very crazy functions that will have a very complicated analytic structure. But we found a way of cheating. The way of cheating is dealing with, not with the answer, but dealing with the integrand of a loop amplitude. The integrand is something that you get before you integrate, right? So you still have to do the loop momenta, but you can find very compact expressions for the integrand, which is now a rational function of the external momenta and the loop variables. So it's a rational function. So what do? You put your z, and then you repeat all this, and you study the singularities. When you have loop amplitudes, you can also have singularities that are not factorizations like these ones, but they are called forward limits, which are the points where the loop momentum can become on shell. And then, from the point of view of an amplitude, it looks as if you had an amplitude where 2 particles had some given momentum, and the other particle had precisely the opposite of that momentum. So it's as if the loop was cut. Okay? So that would give rise to the all loop, what is called the all loop recursion relation, which has a very similar form to this one. Okay? So now I have to make a decision. So we have time either to do us one example, so we can construct the 4-particle amplitude, or we can jump to the twistor string. But the twistor string story, we will not have time to do it in 15 minutes. So we'll have to leave it halfway. So let's do an example, okay? Yes?
Is there a short answer why you need n equals 4 for level between?
Yeah, there is a short answer. The answer is that if you don't have that amount of supersymmetry, the forward limit that I'm describing, the new kind of singularities that appear in the rational functions, will diverge. So supersymmetry allows us to take that limit and as a well-defined residue. Okay. So part of the reason I want to do the example is that is that all this time I've kept this blackboard untouched. And the reason is that we have the 3 particle amplitudes here. And as beautiful as they are, we said that they are 0 when you have physical data, right? Real physical data. And I told you that this is an on-shell recursion relation. It means that if you have an amplitude, say a 4 particle amplitude, I'm claiming that you can build it out of 3 particle amplitudes. But how can that possibly be? If the momenta here are real, you would think, well, you're going to get 0 because you're going to be evaluating the 3 particle amplitudes at some real momenta. But that's where the catch is. We're not going to be evaluating them at real momenta. The 3 particle amplitudes are going to be evaluated at this moment. And this momentum is complex because the lambda of a particle cannot be the conjugate of the lambda tilde of that particle. So let's see how that works. So one example. This is 4 particles. So we're going to compute this amplitude using the recursion relations. Okay. So this is going to be our function a of 0 that we want to compute. So we want to use this formula. Okay. So we use the formula and say, well, this is nothing but the amplitude where I have particle 1 deformed with helicity plus, then particle 2, particle 3, and particle 4 with helicity minus, also deformed. This particle that is here is on-shell. I told you my definition about lines, times the undeformed propagator that comes from this. And the undeformed propagator is nothing but K1 plus K2 squared, where K1 is completely undeformed. So that's the original K1. Now, I have to evaluate this at the value of Z, where the pole is located. So what is the pole? Well, the pole is obtained by asking this propagator to vanish. So that's the particular value Z that I'm going to use to evaluate these amplitudes. So let's compute this. Well, if you write this in a spin or helicity form, we again have this object over here from your notes yesterday is lambda 1 of Z, lambda 2 times lambda 2 tilde, sorry, lambda 1, lambda 2 tilde. Now you see we're using complex momentum. We're going to set this to 0, while this remains completely happy and non-vanishing. So we're going to set this to 0. So what happens? Well, if we use the definition over there, lambda 1 of Z, lambda 2 becomes lambda 1, 2. Now I'm going to use the shorthand notation, plus Z, 4, 2. And we want this to be 0. Okay? So this time, please don't be polite. If I make a mistake, please let me know. Otherwise, we're not going to get the answer. So this equal to 0 means that Z star is equal to minus 1, 2 over 4, 2. Now, there is something interesting. These are 2 vectors. These are vectors in C2. And their cross product vanishes. So that means that at this value of Z star, lambda 1 of Z star is actually proportional to lambda 2. Okay? So that's the version of collinearity. Sorry?
Why is it Z star, not Z?
Oh, because Z is my free complex variable. Z star is the particular value where my amplitude has a pole. Okay? Yes. So, as I said, at Z star, at Z equals to Z star, lambda 1 of Z is proportional to lambda 2. So there is some constant of proportionality. Okay? So let me compute that constant of proportionality. So how can I compute it? Well, lambda 1 of z is this object. So I'm going to put it there explicitly. Minus 1, 2, 4, 2, lambda 4, right? This, I claim, is proportional to this, which you can check precisely by doing the dot product with lambda 2. This was designed, engineered to be 0 by definition. But now I want to compute this coefficient. So to compute the coefficient, well, what would be the best choice? We can dot this, do the inner product with a vector. But what would be the most convenient vector? I would choose lambda 4, right? Because then lambda 4 will wash out all this from here. So I'm going to dot this with lambda 4. Okay? So I get 4, 1 is equal to A, 4, 2. And therefore, A is equal to 4, 1 over 4, 2. Why is that useful? Well, you're going to see. So now, the momentum of the internal particle, okay, which I didn't tell you, but people like to call it I. The momentum of the internal particle I is the sum of k1 at z star plus k2. Okay? So now let me write this explicitly. K1 of z star is given by this, A times lambda 2 times lambda 1 tilde plus lambda 2 tilde. So I can write this as follows. Lambda 2 times A, which is 4, 1 over 4, 2, lambda 1 tilde plus lambda 2 tilde. So isn't that nice? So my internal particle indeed is on shell because p squared is equal to 0, but it's a very complex object, right? It cannot be a real momentum. It's a complex momentum, okay? But I know exactly what the lambda and the lambda tilde of this internal particle are. Lambda of the internal particle happens to be lambda 2, and the lambda tilde happens to be this choice. Okay? Now we're all set. We just have to compute that over there with the help of an eraser. So I hope that while I erase, you are checking my calculation. Okay, so let's use the formulas. We have them over there. Okay, 3 particle amplitudes. They are over there. What do we use? Something here. Now, we have to sum over the helicities of the internal particle. Okay, so let's go back here and say, well, what happens when this internal particle has positive helicity here and negative helicity here? It's 0. I'm declaring that I'm not interested in the F-cube theory. So the only possibility is to have minus and plus. So there is a single term. How nice is that? So a single term, we don't have to sum because the other one is 0. And we just have to use the formula with the labels correctly replaced. That's the difficult part. So we get that our amplitude is, so here comes the challenge. Well, let's start with this first. Times that 3 particle amplitude is plus, plus, minus. So you have to go over there and read it. So it's going to be something of the form 1 hat 2 cube over 1 hat 3, sorry, I, see, I 2. That's the 3 particle amplitude on the left, times the 3 particle amplitude on the right is going to be 3, 4 hat cube over 3i, I, 4. Okay? Well, fingers crossed that I didn't make any mistakes. So again, we know what lambda I is. It's lambda 2 from this identification. And lambda I tilde is this object here, which I'm going to write again. Is 4, 1, 4, 2, lambda 1 tilde plus lambda 2 tilde. Now it's a matter of substituting and remembering that k1 plus k2 squared is 1, 2, 1, 2. So let's substitute just blindly. Okay, that's this times. Now, what's the lambda 1 hat? Well, the lambda tilde of particle 1 was not deformed. So that's very nice. So I can remove the hat. This is the original one. This is the original one. So now I want one with the lambda tilde of the internal particle. But look what happens. So that one would kill this because I'm doing this anti-symmetric inner product. So it's like a cross product. So I'm killing this, and I'm only keeping this. So this guy gives 1, 2. How about this one? Well, in that case, we're not as lucky because 2 only kills this factor, but not this one. So this is the only part that is contributing, and it gives 4, 1 over 4, 2 times 1, 2. Okay? This is looking very weird. So let's keep going. How about the lambda of particle 4? Is that deformed? No. So very nicely, we just remove it from here. And I didn't even bother to put it here. It was a mistake, but it was still OK. So we also have 3, 4 cubed over 3 with the lambda of particle 1. But the lambda of particle 1 is 2. And 2, 4. Okay? So now we start to cancel 1, 2, 1, 2, 1, 2, 3 factors of 1, 2. Cancel the 3 factors we have there, which is good news, because Park and Taylor told us that this function did not depend on lambda tildes. So I started to get a little nervous because we had a bunch of lambda tildes all over the place. But we're not done. We have to see what happens. So we simplify. The numerator is looking good. How about the denominator? So we have a 1, 2 coming from here. We have a 2, 3. So this is all done up to an overall sign. So I'm free to change 3, 2 by 2, 3 at the expense of paying a sign. Okay. Now, this looks wrong. I told you yesterday that we shouldn't have anything that looks like 2, 4 or 1, 3 because those are not physical poles. But very nicely, this cancels with this. Right? And then the last factor is 4, 1, which I'm going to put here. And the reason I'm going to put it there is that it's such a pity not to complete the chain, right? So let's make this a 4 and complete the chain. And this is a Park-Taylor form. Look at the time. Okay, your exercise is to prove the Park-Taylor formula using induction. Assume that the n-1 Park-Taylor formula works. Use BCFW, the construction, and prove it. Okay. Try to do that today because then tomorrow we're going to use it to derive the twistor string formula, but then you will know that it's true. I mean, you don't have to trust somebody. Okay, so let's stop here. Well, the reason was, maybe it's still here. Well, you see, if you want to compute this amplitude, you have several choices. It also works if you have two particles of the same helicity. So you could also have chosen n to be 2. Okay? So it's slightly more difficult to prove, but it's also true. So the two particles can have the same helicity. The two shifted particles can have the same helicity. What is also proven not to work is if you do the completely unlucky choice. This one together with this one. Then there is a pole at infinity, and we don't have a physical meaning for that pole, and we don't know what to do with it. Now, it turns out that if you supersymmetrize all this story, then everything works all the time, because particles don't carry helicity anymore. They are completely supersymmetric, and they carry all the information of all possible helicities at the same time. But then the deformation has to be supersymmetrized as well. Yes?
So to run the recursion to much higher point amplitudes, we have to always make a choice, like when we put higher point amplitudes, but we don't add higher point amplitudes.
Yes, indeed. So what we have done here, or at least I'm trying to give you a glimpse of the fact that if you say, I want to construct a theory of plus and minus helicity, plus and minus 1 helicity particles that is CPT invariant. So I need both, right? On top of that, I want only dimensionless couplings. Then Poincaré invariance or Poincaré covariance tells you that the 3 particle amplitudes are uniquely fixed because of the little group transformation. And the recursion relation tells you that you can complete the complete S matrix from them. So in this way, you can prove that that theory is unique. Now, higher derivative theories are not unique. You have lots of freedom. Okay? So you could try to generalize the construction, but it's not as fundamental. Yes?
You made it sound like I shouldn't think about the U1 decoupling identity as pulling a U1 out of the U1, because, or at least it would seem like if you choose a gluon to be a U1, then you could just see the identity would
Yes, but remember that we first got rid of the structure constants, right? And we ended up with now traces, right? Of course, if you replace the trace of a given particle by the identity, the formula for the structure constant as a commutator will give you 0. So that's what you had in mind, right? No, I'm saying in the formulation where we only have traces, the U1 decoupling identity is the statement that the coefficient of a particular trace, after you set that particular generator to the identity, has to vanish, independently of the other ones, necessarily. Yes. Why one kind of in the part-Taylor amplitude, or in the 3 particle in which one? In the part-Taylor amplitude is you have to work and show it, but you can also try to study different limits where you say, well, I want to study a collinear limit where I set the lambdas of 2 particles to be collinear, but not the lambda tildes, and ask if there is a possible factorization of my amplitude along that channel. If there is a pole, you know that that factor has to be included. If there is no pole, that factor should not be included. So you can follow that exercise and ask for an amplitude that only has pluses everywhere except at 2 places. What happens if I take the limit when any lambda tilde approaches another lambda tilde? Or in more invariant terms, when a square bracket goes to 0. Okay? So physically, this will correspond to some factorization channel. And you can ask, following my rules of which amplitudes, 3 particle amplitudes are 0 and which ones are not 0, does this amplitude blow up or not? And you will find that it doesn't. So you cannot possibly have this in the denominator. Well, if you ask, what's the behavior when I send this to 0, you will find that if b is equal to a plus 1, then there is a pole. And you find that if b is different from a plus 1, no pole. So just from this analysis, you could guess the denominator. Or you could derive the denominator. Okay?
But okay, it's also true that you can write both ways. For example, we are 4-point example.
Well, but that's only true for 4 points.
The other ones also will be much more.
No, the other ones, no. No, 4 points is just, so what Pedro is saying is that at 4 points there is an accident that happens. You can show that this formula, well, it's not really an accident. Well, yes, it's an accident. I mean, I wrote this formula using the Parr-Taylor formula, but see that this guy is MHB, is maximally helicity violating, but it also happens to be maximally helicity conserving, right? Because it has the same number of pluses as the same number of minuses. It's the only case, it's the only MHB amplitude that is at the same MHB and maximally helicity conserving. That means that there are 2 ways of writing it. So I can write it like this, as we got it, right? 3/4 to the 4th with all these factors. Or, and this is an exercise for you, using 4 particle kinematics, and only is true for 4 particle kinematics, this is also equal to 1/2 to the 4th divided by 1/2, 2/3, 3/4, and 4/1. Okay? Well, and the reason is that if you look at your notes, Park and Taylor gave us also the formula when you have lots of minuses and only 2 pluses. But that formula for 4 particles reduces to this. So if everything is going to be consistent, the 2 formulas must be equivalent. Okay? So you can show that that's true by using 4 particle kinematics. Okay?
For 5 points, of course, the left-hand side is still very nice, but couldn't I write an analog of the right-hand side, which would be I would see.
No.
The 5 points starting both from MHB or from MHB bar. Wouldn't there be a representation? Of course, I could simplify it to the left-hand side also, like here.
No, I mean, what you're saying is that if you have 5 particles, what you're saying is that if you have 5 particles, you can always, or any number of particles, so you can always take the Parr-Taylor formula and you can always write it as, let me define SAB to be Ka plus Kb squared. So you can always write it as S12, S23, and so on, with a bunch of factors in the numerator. That's it. But the fact that this guy only has poles in the holomorphic limits cannot be changed. That's just a fact. No, I think you're thinking about the momentum twister version where the object looks very complicated in momentum twisters. You factor out the MHP even though you're doing an MHP, and then there is this other way of running it. Yes. But here, I mean, here is after you multiply by the other factor and everything, it's, yeah. So in other words, in that way of writing the NMHB amplitude, if you have, say, the 5-particle NMHB amplitude, you factor out the MHB1. Now those poles will be cancelled by the momentum twistor numerators. So those poles are not really there.